Data compression can be enabled for SQL Server, Azure SQL Database, and Azure SQL Managed Instance. Database compression improves the performance of input-output workloads, and data is stored in less pages, which increases the speed of queries. Row and page compression can be used for row tables and indexes to reduce the size of the database. And column store compression can be used for column store tables and indexes, and that'll also help reduce the size of the database. Row and page compression can also be configured for the following database objects. So an entire table that is stored as a heap can be compressed. An entire table that is stored as a clustered index can be compressed. An entire non-clustered index can also be compressed. An entire indexed view can be compressed. And interestingly, partition tables and indexes can be configured using compression option for each partition. So compression settings can be different for each of your partitions. When using row and page compression, though, there are some things that need to be considered. One of these is the form of compression that's available for each edition of the Azure SQL database. You should also know that compression is not available for system tables. Compression allows more rows per page, but does not change the maximum row size of an index or a table. So compression can't be enabled when the maximum row size plus the compression overhead exceeds the maximum row size of 8,060 bytes. And finally, the compression type can be specified as row, page, or none. Some further row and page compression considerations are as follows. Partitions and partition lists that are out of range will generate an error. Non-clustered indexes will not inherit the table's compression property. The compression property of indexes must be explicitly set. And finally, clustered indexes created on the heap will inherit the compression state of the heap. Alternative compression settings can be configured. Column store compression. So column store tables always use column store compression, and that can't be configured. Column store archival compression can be used with the following objects: a whole column store table or a whole clustered column store index. We can also use a non-clustered column store index, and partition column store tables and column store indexes as well can also be compressed. When using data compression, there are benefits and limitations that need to be considered. Some of these considerations are as follows. The performance of using column store archival compression is slower than using column store compression. Column store archival column stores use reduced storage, which is not accessed frequently. Partition tables and indexes inherit the data compression of the original partition. So during replication, the snapshot agent will create the initial schema script with the compression settings for both the table and the index. Compression needs to be enabled on both the table and the index. Let's look at Blob data compression. So files can be compressed when stored to Azure Blob storage and decompressed when read from storage. So storing files using compression saves disk space and network traffic, which also helps save your costs. And there's different compression formats we can use, such as dflat, gzip, bzip2, lzo, and snappy. So it makes for cost savings because we can compress our blob storage when we store it, and then we can decompress it when we read it. In this video, I'm going to demonstrate how to create a table partition in a Microsoft Azure SQL database. So partitioning and sharding solve the same goal and can scale similarly, except sharding gives you that additional option of geolocating the shards. But we don't really need that geolocated scale. We can create up to 15,000 partitions, so the table partitioning can handle a high degree of scale itself. So for our purpose, we're only going to create 2 partitions, operational and historical. One additional temporary partition may come into play. On a regular basis, the older records of the operational partition are moved into the historical partition. So assuming our application queries are written correctly, our queries won't hit the historical partition and they'll perform as if our database is very small. So as you can see over here, I'm in my database. Here's my database server along with my database name. I want to expand and I want to go into Query Editor. So we're going to run some queries. I could do this inside Microsoft SQL Server Manager. I can also do it in Query Editor as well. So I open up Query Editor and naturally I pass in my username and password. Click OK. And then I like to kind of push that to one side so I can get my full look. All right. So the first thing we need to do is to create a regular table for a demo. So I'm going to paste in my code here. So we're going to create a table called Table 1 with a PK column, a data column, and a partition column. After that, we're going to alter the table. We're going to add a constraint PK Table 1 as a primary key cluster. Then we're going to populate the table with descending dates. Okay, and that'll give us some data to work with. So if I click Run, the query is running. You can see it down below. Once it gets finished, we should get a result saying everything is fine. And the query did succeed. And we've got 999 affected rows, so we know that there is data in there. Okay? So let's take a look at it. I'm going to come down. I'm going to add the query, select top 40 from table 1. I'm going to run that query. I just want to see the data that we're working with. So you can see it says primary key column is 1, data column is 1, partition column has the date fields in it. All right. So now we need to look at the indexes. So let's show the indexes with the partitions. So if I come down, here's my query that's going to show the indexes with their partitions. Keep this in your clipboard because you're going to run this a couple of times. So we go ahead and click Run. Now it's pulling back the indexes and their partitions. You can see my table has one index name of PK Table 1. There's one partition and all 999 rows are in that partition. So let's go ahead and create a partitioning function and a partitioning scheme. So I come down and I paste in my code. So we're going to create a partition function, myDateRangePF. As a range, right for values, we're going to get the date and we're going to partition out the last 90 days in the past. We're also going to create a partition scheme and we're going to split it out for operational data. So we got two kind of partition. We got a partition function and a partition scheme. The partition function is going to say, all right, we're going to partition everything out of the last 90 days. And our partition scheme, then we're going to kind of split it out operationally. So what's not in the past 90 days is operational data, and we want to select from that operational data. So I'm going to highlight it, click Run. Again, you can run all these queries in SQL Server Management Studio. Okay. So the query has succeeded. I've created my partition function, created my partition scheme. Now let's take a look at the partitions that we created. So I come down, I paste my code in again. So we're going to say select the partition scheme name, partition function name, the boundary ID from our system partition schemes. So we'll run this query and we'll take a look at what results. We can see we've got one partition scheme, one boundary ID, and the value as populated. So let's modify the table to use this partition. So at this point, I'm going to come down, I'm going to paste in my code. It's a little bit longer, and it's going to be an alter table. So we're going to alter the table, table 1. We're going to drop the constraint on PK table 1. Then we're going to alter the table and add a constraint with a primary key non-clustered of PK call. We're going to create a clustered index on the table as well. And once we run this, come up to alter table, click run. This should modify the table to use these partitions. So how do we know if that worked? We're going to come up and we're going to run this one again. This is the query you're going to run multiple times that show the partitions, and they show the indexes that use it. So click run. Now you should see something a little different. We're going to see our main partition, PK table 1, that has 999 rows. But you'll see two more partitions. Partition number 1 has 910 rows, and partition 2 has 89 rows. So this 89 rows, these are our operational, whereas the 910 rows, these are all old. Remember, we said from 90 days back. Okay, so let's populate some future data and see what partition that fits itself into. Ideally, future, we want operational data. So I paste in my script, and the script looks like declare some values, integer values, starting PK values. Then we're going to insert into the table future dates from another month. Okay, so I'm going to highlight my script, click run. We should see a success, and we've got 30 new rows put in. So now let's go up and run our show index again. And this time, we'll see we've got in our regular partition 910 rows, whereas that's exactly what it was previously. And now we've got 119 rows. So we just added those 30 new rows to partition number 2, which is what we want to do. Conceptually, we want to shift the oldest month of partition 2, but there's no migration between partitions. So what we're going to do is we're going to run this query, alter the partition scheme, and we're going to move the partition point 30 days forward. Okay, so let's click the run. Doesn't take very long. It's been succeeded. Let's run our show indexes again and see how they have changed. So click run. Once we get it back, now we see a little different. Okay, now what we're seeing is our partition 1, which is just, all of our records. Then the partitions that we created, partition 1 has 910 rows. Partition 2 has 30 rows. So this is the new monthly split that we just did above. And partition 3 has 89. So we want to merge what's in the partition containing this low boundary into our operational data. So we'll run another script here that basically we're declaring the lower boundary as date and time, and then we're doing an inner join on these values. Then we're altering that partition function to take in the new range. So click run. Query has succeeded. Now let's go back to our trusty show indexes again. Click run. And now you'll see they've merged them in together. All right, we've got 940 history that were merged into history. And we've got our 89 operational. So if we want to prove that partition 2 is back into operational, I can come down and I can insert into the table some more values. all right, some present day values. These should not go into partition 1, they should go into partition 2. So if I run the query has succeeded. I need to go and run my indexes again and take a look at where they're all to. So you can see partition number 1 still 940. And now partition number 2 has 90, whereas before it had 89. So we added a new value to the table and it went into the right partition. So I hope this video showed you how to kind of take your data, partition it up into multiple different partitions, and as a result, it can make your queries much faster, because every time now that we want to query our operational data, we don't have to worry about all this old partition data. So once, right before we leave, I like to take a quick look at the full script as a whole, because sometimes when you're in SQL Server Editor, it makes it a little bit difficult to look through. But what we're doing here is we're creating our table. We looked at the dates from the table because we put some dates in. We showed the indexes with their partition. We created a partition function scheme to partition out 90 days in the past. The rest is an operational split out. We looked at our partitions. We modified the table to use the partitions. Then we ran the show indexes again to look at how the older rows went into the first partition and the newer ones went in the second. We populated a future data for another month, ran the show indexes again, and you can see that the new rows went into partition 2. We shifted out the oldest month of partition 2 into partition 1. We ran the show indexes script again, and we saw that we had that newly split month into a new partition. We merged that low boundary with the next adjacent date permission partition. Then we ran our show indexes again to see that the old ones were merged into history. Operational was still fine. Then we inserted a new value. Then we checked, and then sure enough, it did get inserted into partition 2. So I hope this video showed you how to partition your data. So again, it improves efficiency, it improves scalability, and it's just a good idea to do with your SQL databases. Let's take a look at the concept of sharding data. So sharding is a method for distributing large amounts of identically structured data across multiple independent databases. Some reasons for sharding include the amount of data may be too large to fit within a single database due to the limitations of that database. The number of transactions that will be sent to the database may exceed the number of transactions that can be handled by the database. Tenants may be required to be physically isolated from each other. And database sections may be required to reside in different parts of the world for compliance, performance, or geopolitical reasons. Databases can be scaled as the demand on them increase or when new customers are brought on board. There are two types of scaling that can be performed. Horizontal scaling. Horizontal scaling is when we add or remove databases to kind of react to changes in traffic. So we're going to use it to fine-tune the performance and capacity, and this can be achieved through sharding. And this is also known as scaling out. Conversely, vertical scaling refers to increasing the compute resources or the storage resources of a database. So we're going to size up the instance that we have to a bigger size, as opposed to horizontally, when we scale out, we add more. The Shard Map Manager is a collection of shard maps. The Shard Map Manager instances manages data in 3 places. The global shard map is stored as a designated database that creates special tables and stores procedures to store all the shards, maps, and mappings. The local shard map is created in each database that's designated as a shard and contains tables and stored procedures to manage the shard locally. And finally, each application instance has their own application cache that stores recently retrieved routing information. If we're going to shard up our data, we need to know where to go and find it. Shard maps can be created as a list of individual shard key values or as a range of shard key values. The list shard map is used to associate the identified shardlets and the databases that serve that shard. List mappings are explicit and multiple key values can point to the same database. We also have the range shard map, and that's defined by using a key range that's defined using a low and high key value. Multiple ranges can point to the same database. Databases can be created and configured to store multiple tenants or clients on one single database, and then they can own their own individual databases if they want. Single tenant databases refer to having a single tenant or client on their own database and provides data isolation, backup, and scaling for single tenant. Single tenant databases use a list shard map. Multi-tenant databases store multiple tenants of clients on a single database, and database rows contain a key that identifies the tenant the record belongs to. Now let's discuss the process of designing our tables. Designing a database structure is important for storing the correct data that will be needed for future data analysis and will also allow the data to be queried effectively and efficiently. So getting the proper database structure right in the beginning will save you a lot of time and effort and money in the long run. There's also table persistence or data persistence. So there are different levels of data persistence depending on how long the data needs to be stored. Does it need to be stored a long time for compliance reasons, or is it just temporary data that we use and then let it go and forget about it? Right, so we have to take that into account as well. Database schemas are an effective method for grouping tables that are related, and these are extremely useful for multi-tenant environments. So if you got multiple tenants using one database, a database schema is highly recommended. And distributed tables. So dedicated SQL pools can operate on tables across distributions. There are several available distributed table options in Azure, and they're great to take advantage of because these dedicated SQL pools can span across multiple distributed tables all across a distribution. Star schema tables. So the star schema pattern has tables for storing facts and dimensions that can share a common key for associating facts and dimension data. We have fact tables. These store quantitative data that are common in transaction-based systems, which are loaded into dedicated SQL pools. An example will be an online store, for example, that generates sales data, which can be loaded into a dedicated SQL pool. Dimension tables are used to store attribute data. This data can change occasionally. An example of this is the name and address of a shopper. Right? Their address could change over time. Their name can also change over time. And integration tables. These tables are used for staging data. We may be getting ready to pass that data onto a different system. And these tables can be regular or external tables. So what are some benefits of using a database schema? Database schemas are an effective method for grouping tables that are related. And again, like we said before, they're great for use in multi-tenant environments. Some advantages of using a schema include database security. So security permissions can be created and assigned for database objects based on a user's access rights. Schemas permit database objects to be organized into logical groups within a database. A single schema can be used in multiple databases for logically grouping related database objects. And the ownership of schemas can be easily transferred, and database objects can be easily moved between schemas. So it makes the ownership and management much more simpler as well. Let's discuss table persistence. So there are different levels of data persistence depending on how long data needs to be stored. Again, it could be for compliance reasons that we need to store it for a long time, or it could be just temporary data that we use and then let go. So let's look at how table persistence interacts with some different tables that you can find in Azure. Regular tables are used to store data using Azure storage, and that data persists whether the session is open or closed. Temporary tables are only available for the session duration and can be used for storing temporary results and use local storage for increased performance. Temporary tables are great because they remove themselves when the session ends and there's no need to perform any manual cleanup. So this could be just session state information that we want to store, but we don't want to persist it over a long period of time. And we also have external tables. So these are used to link with data stored in an Azure storage blob or Azure Data Lake store. External tables are great for loading data into dedicated SQL pools. Distributed tables. So we mentioned how distributed tables are great because a SQL pool can work over a group of distributed tables. These tables can be used by dedicated SQL pools to store and perform operations on them. There are 3 supported dedicated SQL pool methods. The first are hash distributed tables. They're used to distribute rows based on the value in the distribution column and accomplishes high performance queries on large data sets. We have replicated table stores. These store full table copies on each compute node and require extra storage too, and also allow for fast queries since there's no data movement. Replicated tables are not useful for large data sets. And round-robin tables are used to quickly and randomly distribute data rows evenly across all distributions. This way, performing queries will require the most amount of data of all the methods, but you get significant performance increase because we're distributing that data evenly across all the distributions. There are several important database features that also need to be considered. First of all is the use of table partitions. So table partitions are used to store and perform operations on the table rows based on a data range. Tables can be partitioned by, say, city, column, state, or year, depending on what your data set is, and it allows for increased query performance by limiting a query to data within a partition. Column store indexes. So tables are stored as column store indexes by dedicated SQL pool stores, and that allows query performance and high data compression on large tables. And the query optimizer. The query optimizer uses column-level statistics to create query execution plan and utilizes statistics on individual columns and columns used in query joins. So if we're running big queries on heavy sets of data, it allows us to optimize that query and really utilize statistics on individual columns and the columns that we're using in the query join to make our queries much better and much more efficient. In this video, I'm going to demonstrate how to implement Geo-Redundancy with your Azure SQL database. So once I'm in the Azure console, I can come up and choose SQL databases, and I should be able to find my previously created SQL database. Here it is here. Right now, it's just a basic database. You can see there is no replica type. So we need to go ahead and start the Geo Replication process. So let's click the database and go into the specific console for this database. And on the left-hand side, we're going to see something called Geo Replication. So the whole point of Geo Replication is to replicate our database to a completely different region. Right now, we're in East US. If something ever happened to East US, the whole region went down, then our data would be lost. So we want to replicate that globally so that if the unthinkable does happen in one region and you lose all availability zones, we can still go to our geo-replicated database on the other side of the world or in Canada, where hopefully everything is okay. So let's come down on our database. You'll see my SQL database here. I'm going to come down to geo-replication on the left-hand side and click geo-replication. This brings us into a console that we can see the target regions that we can deploy. So right now we're in the primary, East US. My server is Richard K. Spencer. My database is listed as well. We have no failover policy, but the status is online. So if we look at secondaries, it says geo-replication is not configured. We need to pick one. So I'm going to pick Canada Central. I want to create another version of this database for reads in the Canada Central region. So once I click that, it comes into region. It says Canada Central. My database name stays the same naturally. My secondary type is readable, right? So this is readable. It should asynchronously sync. And not only now do I have high availability, but I can offload some of the database reads to this secondary read replica. Now it's asking for a target server. So I have to create another server in that region to sit this database on. So I'm going to call it Richard Geo-Replicate.database.windows.net. When you set these up, ensure that you give it a good name and descriptive name so you can kind of keep track of them all. I'm going to give it the same login as the previous one. Make sure I type them in correctly and they match. And I'm going to click select because you see your location is already selected here. So we click select. Now our target server is filled in. If we had an elastic pool to pull from, we can incorporate that here. And my pricing tier is here. So my pricing tier, right now it's 5 for basic, and the data max size is 500 megabytes. And this is a mirror of my original database. So I'm going to click OK. I'm going to click OK again, and you'll see my deployment is in progress. So it takes a little bit of time to deploy this database from your primary region to a different geographical region. So you'll see up here, you'll see under the bell, you'll see your deployment in progress. When this happens, you'll get a green light, much like these below, that tells you that your database has been replicated. So we'll just sit and wait, and it shouldn't take too long. And when it comes back, we should have a geo-replicated database in Microsoft Azure. As you can see now, as the deployment progresses, you can see now I do have a secondary in Canada Central. You can see the storage name and the database. It's not complete yet, right? It's still moving through the process of the actual replication. So as you can see, the deployment has succeeded. I have my green check mark. Right? I can click on the resource to go right to it, or I can dismiss it, come back to geo-replication, and look and see now how the changes has happened. I do now have a secondary in Central Canada. So if I come back to SQL databases now, and I do a refresh on this page, you'll see now I have two databases. I have a database server, Richard K. Spencer, which hosts this database, and I also have a replicate in Canada Central that hosts my replicated database. So now if something were to happen in our main region, we have a geo-replicated in Canada that we can go back to and kind of use if our main database goes down in East US. Right, so this will be a catastrophic event where you would lose multiple availability zones within a region, we still have another region that we can back up our database to and keep a synchronous copy, and we can revert to that database should we need to if disaster strikes. So it's a great disaster recovery mechanism. So if we want to look at failover technology, we can come back to Home, find our SQL servers, find our main SQL server and main database. Then we come down and we look at failover groups. So we have to create failover groups in order to automatically manage that replication. We can failover manually. We can also create a failover group. We can call it test failover RS. We can call it Richard Spencer fail. We have to configure our secondary server. So which one do we want to fail over? That would be our Geo replicate that we created. What's the read and write failover policy? Is it going to be automatic or is it going to be manual? And what is our grace period? So we can set that anywhere from 1 hour to 24 hours. And then within that group, we have to select a database. So we're going to select our Geo replicated database. Click OK. Then we click Create. We have our failover group being created. And basically, we just told Azure that if this database server, Richard K. Spencer, and the databases fail, I want you to fail over to the Geo replicated version. So it's still working on the deployment. And once that deployment gets done, you'll get your green check mark. And now we've incorporated Geo-Redundancy and a failover group to kind of take advantage of that Geo-Redundancy feature automatically for us. So once it's done, you can go to your resource group or pin it to the dashboard. We can go ahead and click it, take a quick look at what we deployed, and we deployed another failover group. Just like we mentioned earlier, this is a failover group. So now our failover should be perfectly fine. If we lose a region, we should automatically fail over to another region using our Geo redundancy and our Geo redundancy failover groups. So I hope this video kind of showed you how to enforce disaster recovery with high availability in using Geo redundant databases. Now let's discuss redundancy. In particular, file and blob data redundancy. So file and blob data redundancy ensures that your storage account achieves its availability and durability targets for both planned and unplanned events. This could include hardware failures, network outages, power outages, and massive natural disasters. Azure Storage Account replicates data 3 times in the primary region, and there are 2 options for replicating data in the primary region. First is locally redundant storage. So this will copy data 3 times synchronously in a primary region for a single physical location, and it's the cheapest replication option available. This method is not suggested for applications demanding high availability. We also have zone redundant storage. So this will copy data synchronously across 3 Azure availability zones in the primary region. This is recommended for applications demanding high availability, because if one availability zone goes down, you still have other availability zones where your application can be deployed or is deployed. Microsoft recommends this method in the primary region as well as copying data to a secondary region in case it's a natural disaster where it takes out multiple availability zones, or a massive power outage where multiple availability zones go down. If you're using a different zone, then that may be on a different side of the country, and you could take advantage of those availability zones if they're still up and running. Locally redundant storage. Locally redundant storage, or LRS, copies data 3 times synchronously in a primary region for a single physical location. And again, as mentioned, this is the cheapest replication option. Write requests that use locally redundant storage return successfully once the data is written to all 3 replicas. This is known as replication confirmation. To mitigate this risk, Microsoft recommends using zone redundant storage, so storage across multiple zones, geo-redundant storage, or geo-zone redundant storage. So what are some use cases for locally redundant storage? Firstly, locally redundant storage can be used for data loss prevention. Data can be reconstructed in case of a catastrophic failure. So again, it's not high availability, but that replication will keep us going and our data will still be persisted. If we lose one or two replicas of our data, we still have 3 in our local zone. It can also be used for regulatory compliance. So due to these regulatory compliances, data may be restricted to being replicated within a country or a region. So it has to stay local. So locally redundant storage is a good option to ensure the company is staying compliant. Zone redundant storage. So zone redundant storage is used to replicate data synchronously across 3 availability zones. These availability zones are in the primary region that you're using. These availability zones are located in different physical locations of that region, and they have their own power, networking, and cooling capabilities. So it's 3 different data centers within your region. Zone redundant storage is great for data durability and your applications that really need high availability. Write requests made to a storage account that uses zone redundant storage occurs synchronously and will only return a success status once the data is written to all 3 replicas. Zone redundant storage is recommended as the primary region for scenarios that require consistency, durability, and high availability and have to meet regulatory requirements. Secondary region redundancy. So what happens if the region you're using and all of the availability zones within inside that region goes down? That's why we need to have secondary region redundancy in some cases. This can be used to increase the high availability of your application because your data is then replicated in a totally different geographic region than your primary region. This could be in different parts of your country or in different countries altogether. This allows your data to be durable in case of a regional outage or disaster in the primary region. The secondary region is determined based on the selected primary region. So you determine what you want to use as a primary and a secondary region. Secondary region redundancy storage. So there's 2 options for copying our data to that secondary region should we want to go that route. First, we have Geo-Redundant Storage. So Geo-Redundant Storage, or GRS, copies data synchronously 3 times within a single physical location in the primary region using locally redundant storage, and then asynchronously copies the data to a single physical location in the secondary region. You can also take advantage of GeoZone redundant storage, which copies data synchronously across 3 availability primary region zones using zone redundant storage, and then asynchronously copies the data to a single physical location in the secondary region. So you can have geo-redundant storage, where you have local redundant storage stored 3 times within one region and then to a secondary region, or geo-zone redundant storage, where your data in your primary region is copied to 3 different availability zones and then on top of that sent to another secondary region. So you're ensuring that high availability and that data durability and ensuring compliance all at the same time. In this video, we'll determine the appropriate distribution scheme for an Azure Synapse Analytics database and build it into the table upon creation. So once we get into our Azure console, we have to go to Azure Synapse Analytics. So we'll click Azure Synapse Analytics, You should have your workspace created. But if you do not have a workspace, you just click New. We select our subscription, any resource group that we may be using. We enter a workspace name. So I'm going to say Richard K. Demo. Make sure it's unique. Then we have to select the data lake storage generation too. So we can use it from subscription. So I'm going to use the pay-as-you-go subscription that uses my pre-created account and my pre-created file system. So I'll click Review and Create. And I'll look through my information. I'm creating a Synapse workspace. I click Create. I'm still using that same storage account. I'm just creating a Synapse workspace for us to use. Okay. So that deployment will take a little bit of time. Once it's deployed, you can come back into Synapse Analytics again, find your deployed workspace, click it to enter, and then I usually just collapse the left-hand side. Then you must create a new dedicated SQL pool. So click New Dedicated SQL Pool, give it a name, and then you can bring your performance level down for a demo, increase it as you need it. I like to keep it down just for keeping costs down during demonstrations. Click Review and Create. You see everything that you've created there, and this is your SQL pool. So we go ahead and click Create, and that deployment will take effect. So once that's all done, we can come back to our Azure Synapse Analytics again, find the proper Synapse workspace, and then come down on the left-hand side and you'll see SQL pools. So click SQL pools. You'll see your built-in SQL pool. You'll also see the SQL pool that you created. Okay, so they should be two there. There should be the serverless built-in SQL pool and the dedicated SQL pool. So I want you to come back to Azure Synapse Analytics. Make sure you're in the correct namespace. Come down to SQL pools again. Click your dedicated SQL pool that you want to work on, and then click Launch Synapse Studio. And this is going to launch our Azure Synapse Analytics. From here, we have to decide how we're going to set up our table, right? So distributed table appears as a single table, but the rows are stored across 60 distributions. We can use hash distributed tables, which improve query performance on large fact tables. And that's what we're going to do in this demonstration. We can also use round-robin tables, and they're good for improving loading speed. So hash distributed tables distributes table rows across compute nodes by using the deterministic hash function. So first thing we need to do is come up and click New, and we're going to click SQL Script. We're going to design our table right now with SQL Script, and we're going to incorporate that distribution. So there's identical values always hashed to the same distribution. SQL Analytics built in some knowledge of the row locations. So in dedicated SQL pools, this knowledge is used to minimize data movement during queries, which also works to improve query performance. So I'm going to put in my script, and let's talk about it. So basically, I'm just creating a table called Fact Internet Sales. It has the columns product key, order date key, customer key, promotion key, sales order number, order quantity, unit price, and sales amount. So you'll also see I'm creating a clustered column store index, and I'm specifying that the distribution to be a hash distribution on the product key column. So choosing a distribution column is an important design decision because the values in this column determine how the rows are distributed. So the values in product key is going to be the determining column on how the data is distributed across the compute nodes. If you don't choose the best column the first time, you can recreate the table with a different distribution column. So come up to Connect To and make sure you're connected to your dedicated SQL pool and not the built-in serverless one. So click your dedicated SQL pool and then run your script. So once you run your script, query executes. The query executes successfully. Now you've created your table, fact internet sales, using hash distribution on the product key. So your next steps are now to fill in the data for the database and then let that distribution take hold and let the distribution kind of distribute that data across all the compute nodes based on that product key column. So I hope this video helped understand distribution, choosing a proper distribution, and incorporating that distribution when you create your table. In this video, I'm going to show you how to archive a blob storage and then rehydrate that storage as needed. So the first thing we want to do is come into our storage accounts and click the storage accounts. Find your specific storage account. Here's mine. It's the type storage account. It's a storage V2. So I click my storage account. And normally then I collapse this left-hand side and I can look at my storage account. So we want to go into containers. Containers are where we are going to upload our file, archive it, and then rehydrate it. Okay, so our container is here. I called mine Richard FS. So I can click it. And now I'm brought into my container. You see I already have one file in here. I'm going to upload another file. So I click the upload button. I select my file. And I come to desktop. And I want to take an image file. So I'm going to take download.jpg. Under advanced, I can look and specify my block type, the block size, what the access tier is. So I'm going to leave that as hot right now, and I'm going to upload it. Upload has completed, so I can clear this screen. And now I can look at my download.jpg. Right now, the access tier is hot. So that means that it's going to be used, right? We have hot tiers and cool tiers, right? So now what we want to do is take this download.jpg. We're going to change that tier from hot to archive. So we just click change tier. Under access tier, we click archive. And now it tells you that setting this access tier to archive will make your blob inaccessible until it's rehydrated back to hot or cool, which may take several hours. So I'm going to go ahead and click save. Successfully updated the access tier. So right away it's in archive. It doesn't take long to put in the archive, depending on the size, but it may take a little longer to rehydrate it. So now that it's in archive, let's rehydrate it. So click the image or the file that you want to rehydrate. Come back up to change tier again. You'll see it's in the access tier. Here we can rehydrate it. So when we rehydrate blobs out of archive, we rehydrate them into hot or cool tiers. And they're charged as read operations. So high priority has a higher operation and data retrieval costs compared to standard priority. So let's bring this back to the hot access tier, and now you'll see the rehydration priority. So standard is normal. High priority gives you just that, right now, a much higher priority, but it also show up as a separate line item on your bill. So we're going to choose the standard rehydrate priority. It's telling us that rehydrating a blob may take several hours to complete. We're going to go ahead and click save. And now it's successfully updated the access tier. We can do a refresh. You'll notice it's still in archive. So let's click the file again. and you'll see a little notification that says this blob is currently rehydrating using standard priority and can't be downloaded. So once that's finished, it's back into hot storage again, and then that would be an example of archiving, then rehydrating our blob level storage. Okay, so let's come back. We can close this window. We can refresh. It's still rehydrating. So this may take some time. So once it gets finished, we can take a look again and see what tier it is in after it's done rehydrating. So it's been an hour. That's because we're using standard priority. If we used high priority, it would guarantee an hour retrieval process for under 10 gigabytes. So we're using the standard. This could take up to 15 hours. Right now I'm an hour in. If I keep refreshing, it still says it's hydrating and can't be downloaded. It can't really have anything done with it. So keep that in mind when you try and pick a rehydration priority, whether it's standard or high. How quick do you need that archive data? So when this gets done, it'll be back into my hot storage and I can use it as I need to. Right, so it's a good option for moving files in and out of archive, files you're not going to use anymore. And if you decide you do need them again, you can pull them back out. But remember the time that it takes for standard priority versus high priority and the pricing difference involved in between the two. So I hope this video showed you about archiving and rehydrating files, some of the different options, and some of the different pricing implications that go with that. In this video, I'm going to demonstrate how to set up data retention policies within your Azure SQL Server database. So once we're in the Azure console, find the SQL Server that you want to create your data retention policy for. I'm going to use Richard Geo Replicate, and it's located in Canada Central. So this is a replicate of my Richard K. Spencer database. So I'm going to configure data retention on this replicated database. So I click the database that I want to configure, and then on the side here you'll see backups under settings. So go ahead and click backups, and let's collapse this left hand side to give us a bit more room. So right now you'll see there's no restore point available and there's no available long-term retention backups. So let's come up and click retention policies. And under retention policies now we have to click the database that we want to configure the policy for. So once we click it, come up and click configure policies. And here's where we can configure our policies. So how long do we want point in time restore backups to be kept? So we can keep them from anywhere from 1 day to 7 days. Then we get into long-term retention. So how long do we want to keep our long-term retention backups? I can keep weekly backups for 25 weeks. How long do I want to keep the monthly long-term retention backups? So I can keep the first backup of each month for 1 year, and then annual backups. So yearly long-term retention backups, I can keep an annual backup for say 5 years, right? And we're going to use a weekly backup of week 1 of the year that we would like to keep. We can also change this to say week 52, and then that way we're taking the last backup of that year as our annual backup. So we set our retention policies. We've got point in time restore backups that'll be kept for 7 days. We're going to keep weekly backups for 25 weeks. We'll keep monthly long-term retention backups, and we'll keep the first backup of each month for 1 year. And we're going to have yearly long-term retention backups, and we're going to keep an annual backup for 5 years, and we're going to use the last week of the backup year. So we got that full picture of that full year. So if I click apply, it's going to ask me, do I want to apply these policies? I'm going to go ahead and click yes. You'll see the deployment initialize. Now the deployment is in progress. Once it completes, we'll have a little green checkbox here. and then we should be able to view our retention policies. So we'll close out the notification bar and we'll just wait. You see the validation has passed. You'll still see a little bar going across your notifications, so the deployment is still in progress. Just a good way to check on your deployments and see if what you're doing is actually completing. As we say that, the deployment has succeeded. So if I come back now, you can see these values have changed. So I got a point in time restore of 7 days, a weekly long-term retention plan of 25 weeks, monthly long-term retention of 1 year, and a yearly long-term retention. We're going to keep week 52 for 5 years. So I can remove these settings if I wish. I can come back in and reconfigure them and make changes to them if I wish. Once we come back to available backups, now at this point, backup will be backed up automatically. And as these backups become available, then we can use them as a restore point and back up these databases. Right, so I hope this video showed you how to create your retention policies, why you'd want to create your retention policies, and how to configure these retention policies so that you can configure and manage your automated backups in Azure SQL Server. So in this course, we've examined how to plan and implement an efficient physical data storage structure. We did this by exploring considerations for implementing data compression technologies, partitioning and sharding data, designing tables in an Azure Synapse Analytics. We also looked at database and file blob data redundancy, implementing distribution schemes and data archiving, and configuring long-term retention policies for an Azure SQL database. In our next course, we'll move on to examine how to plan and implement an efficient physical data storage structure.